So problem 8.1 gives us that alpha is increasing monotonically and alpha prime is integrable on the closed interval AB. It also gives us that f is bounded on the closed interval AB. So it wants us to prove that f is integrable on the closed interval AB if and only if f alpha prime is integrable on the closed interval AB. All right, so on the worksheet, it started the proof for us. So it started out by saying, choose any epsilon is greater than 0. So since we know alpha prime is integrable on our interval, we can say that there exists a partition such that the upper sum of p alpha prime minus the lower sum of p alpha prime is less than epsilon. So part A, we're going to start out by using the mean value theorem. So by the mean value theorem, there exists some point ti in a closed interval x sub I minus 1 to xi such that alpha prime of our point ti equals alpha of xi minus alpha of xi minus 1 over xi minus xi minus 1. And that's just the mean value theorem, right? So basically, alpha prime of ti equals the change in alpha I over the change in xi. So you can multiply both sides by the change in xi, and you would get alpha prime of t delta xi must equal delta alpha I. So if those two things are equal, then we know if we multiply both sides by the sum of f of si, that they'll still be equal to each other. So that proves what we wanted to prove. The sum of f of si delta alpha I must equal the sum of f of si alpha prime ti delta xi. For part B, we started out by defining m as the sup of absolute value of f of x. So we're looking to prove this thing on the bottom here, right? This big inequality. So we're going to start by just considering the left-hand side of that inequality, that big equation. So by part A, we know that this piece of the expression is equal to this. So I just substituted that in and kept the second part the same. So if you look at the two pieces of this, we notice that this and this and this and this are the same. So instead of having two summations, I turned it into one summation. So they both have the sum of f of si. Then this one has delta prime of ti minus this one has delta prime of si. So that's where this piece right here came from. And then they both have delta xi. So that's where this last piece came from. Okay, so we turned that expression into a slightly smaller, nicer looking one. So now we're going to look at what this has to be bounded by. So in the beginning, we said that m is the sup of absolute value of f of x. So no matter what si is, it has to be less than or equal to m. So we can say that this expression has to be less than or equal to m. And then the second half of this expression, right, this right here, we know from what we're given in the beginning of the proof that the upper sum of p alpha prime minus the lower sum of p alpha prime is less than epsilon. So that's basically what this is right here. So this has to be less than epsilon. So we can replace this with epsilon. So that proves what we're trying to prove. Our big long expression must be less than or equal to m times epsilon.